So just to recap from our last video, we were ending on what the structures look like. And so when we get down into this chloroplast, what we're looking at here is a double layer organelle with these stacks inside. And these stacks are what we call the granum. And they're stacks of these like smaller little green discs that we call the thylakoid. And the red area means that there's a lumen, and that just means an open space. And the thylakoids are important because this is where that cellular photosynthetic process is happening. But let's look at what's going on inside these chloroplasts, because the chloroplasts house many pigments. So the pigments that we want to look at are really important for this process. So when we think about pigments, whether they're photosynthetic or other pigments, basically chemicals that absorb some colors in a rainbow more than others do. So we're going to talk about the rainbow for a few minutes too, to kind of talk about different type of pigments. Colors least absorbed, so the colors that might be least absorbed by a particular chemical or a particular cell are reflected the most. So what we see of colors of things isn't being absorbed. What we're actually seeing is the reflection of that color. So for example, if you're sitting here at your desk and you're seeing something on your desk or on your table or wherever you might be working right now, for example, I have a water bottle in front of me and it's kind of a pink color, but what I'm actually seeing is what's being reflected the most to me. So of the rainbow colors, which we'll look at, what I'm actually visually seeing with my eyes is what's being reflected towards me. The rest of the colors in the spectrum of the rainbow are being absorbed by that object. So when we talk about energy kind of waves, this is important because when we talk about different types of colors of the rainbow, they have different waves. And so basically we can have wavelengths. And now a wavelength is from one peak to the next peak. And the peak is actually what we call the crest of the wavelength. And then the part that's kind of that dipping down area is what we call the trough. But the wavelength of one single wave, and we were to measure this to the distance of the next wave's crest, or we could do the opposite and measure the trough, that's creating an actual single wave of the wavelength. So talking about the rainbow, here is an example of the rainbow. The rainbow is made up of Roy G. Biv. So that might be a way to remember it. So Roy, R-O-Y, G, B-I-V. Now, Roy is red, orange, yellow. G is green. And then we have Biv is B-I-V, blue, indigo, violet. So if we were to look down here, you can kind of see here's that spectrum of the rainbow. So here's red, orange, yellow, a big area of green, kind of a lighter blue, darker blue, and kind of that indigo, and then we get to this violet. Which is kind of more of a purple color. And if you look, so this is what we consider our visual wavelength to what we can actually see. It only falls right in here, right? So we have this visual kind of spectrum that we can actually see, but it's in this very small area. And if you look at this, there are other wavelengths here. So this is a radio wavelength. You can see the top of one crest to the other is very long. We'd have to a long measurement here. So this is a longer wavelength. As we move to the left, we have other things that you may have heard of. So UV light, which is important because again, that's still coming from the sun, that can affect us. So there's UVA and UVB that come from the sun, X-rays, gamma rays, etc. And as you can see, what's happening on this side, so the left side of the visual spectrum, is the wavelength is shorter. So we have shorter wavelengths when we get down this way. Both spectrums, when we get to past visible or on the left or the right, is exactly that, non-visible with our actual eyes. And the radiation that we're getting is only existing from the different wavelengths that are here. And this is what we call electromagnetic radiation, which includes our visible light, so what we can actually see with our eyes. So if we kind of look at this a little bit more, specifically pulling out this wonderful area here. I know it's flipped backwards and red's over here and purple's over here, violet I should say. But this is specifically at our visible light. So our Roy G. Biv spectrum. So here is our red, go all the way over to the violet. Now we said at the red end, the wavelengths were longer, and they are. So they have more kind of space in between each wave crest. Over here in violet, though, you can actually see they're getting smaller between them. So that kind of gives us this idea of that this is where infrared would be going the other direction, and then this is UV and X-rays. This is light energy. So this is less energy. So red is less energy, and by the time we get all the way to violet, we're using more energy. All right. Now the other thing to think about is just kind of looking at those wavelengths. If we pull them out specifically, red has kind of, again, longer wavelengths. Here's orange, yellow, and as we kind of get to green, you'll see that the wavelengths are getting shorter. By the time we get to that violet, they are much shorter. So we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 crests in violet. We're up here at red. We have 1, 2, 3, and the top of a fourth crest of our wavelength. But this is really important because we want to know about what plants can absorb. They know that they are taking that visible light in from the wonderful sun, but they need to look at how does that pigment kind of get absorbed, or how is it kind of reflecting, etc. So there are basically 4 different types of pigments within our plants. So I'll just use my pen here. We have what we call chlorophyll A. We have chlorophyll B. We have beta carotene, which you probably have heard of before. And then we have what we call xanthophylls, which we're not really focused on this particular visual here. But we have chlorophyll A, which is kind of a green. Chlorophyll B is another example of green. Beta carotene is going to kind of be like over here more in the orange area. And each pigment is very unique, and each pigment has a specific spectrum. So let's see, this is important. So the straight line, kind of fulfilled line here, is chlorophyll A, okay? This kind of dotted line, little hash marks, is chlorophyll B, and then the kind of little polka dots are beta carotene, excuse me. So it kind of shows you the absorption spectrum. So where can we absorb the most? So when we're looking at chlorophyll A, you can see it kind of peaks up here, okay, way up top, the absorption of light. And again, if you kind of come down our graph here, it's maybe about 425-ish or so is where it peaks. And then you'll see there is a secondary peak usually for these guys. So not only is it kind of in that green area, but you can also see that it peaks over here about 660 maybe or so, where again it's going to do a lot of absorption. So that tells me that there's some doing absorption of that chlorophyll A. Now chlorophyll B, you can see peaks way up here, much higher on the absorption of light, and again it's a little bit, the wavelength over here is a little different, so you can kind of see there's a difference. And then you can see beta carotene does kind of spike up here. You can kind of see it's hard to see up here. It has a secondary spike kind of over here in the green, and then it actually does not over here. Okay, not anymore over in that spectrum. So let's look at this as a visual. It might be a little bit different and a little bit more helpful. So relative absorption here, they just kind of colored it. So chlorophyll A is a darker green, chlorophyll B is a lighter green, and then the carotenoids, the beta carotenes, are orange, obviously. So it just shows you that spectrum of where things are absorbing. So if they can absorb this particular color, so for example, if we go, okay, here's my chlorophyll A again, and it can absorb here. So that means it's absorbing, it can absorb this kind of area here. And there's a kind of a peak down. It doesn't do too much absorbing in the green area because that's the pigment that it is. But when it gets back up here, it can absorb again in there. So when it's absorbing something, remember, it's reflecting other colors. So if it's absorbing kind of some of our violets and our indigo and blue, and then again it's absorbing a little bit of the kind of orangey and red, what is it able to reflect to us for us to see? Well, it reflects everything in the middle here. So some of that blue, and then kind of over to this a little bit of the orange, which makes sense because most times plants are in this range, right? As we get to fall, they actually change into different colors over here. So again, the same thing with the chlorophyll B. All right, it's absorbing down here, and again, that same range almost here to here, again, where it's reflecting those colors at us. All right, and then again it spikes over in this area. So it's just the area in which reflection is what we see, absorption is what is being absorbed, the color that's being absorbed. So when you look out your windows right now, we are in the season of fall, and so what's actually happening is that the tree leaves are changing color, and that has to do with what's happening within the plants. So the plants are changing, and they know that basically they need to harness everything that's left. So they're going to harness all the sunlight that they possibly can have, and they're going to convert it into chemical energy, into glucose, and that glucose is going to leave the actual leaves, and they're going to move to inner parts of the tree so the tree can stay alive through the winter, because the tree is now going to go dormant. But what happens before those leaves actually fall off is the pigments are starting to go away. And the pigment that starts to leave first, obviously, is the chloroplast. In the chloroplast is primarily the chlorophylls, the greens, the A and the B. And so what you get left on the tree is the rest of those wonderful colors. So the carotenoids, the xanthophylls, and so that's why all trees are different. Some of them have orange leaves, some of them have red leaves, some of them have yellow leaves when they start to change their colors, and what you're actually seeing is the other pigments, okay? You're seeing all these other pigments because the green is gone. This is all gone, and so what you're kind of seeing is a spectrum here of the pigments that are kind of left inside the leaves, and eventually the leaves might just turn brown. Obviously, they're going to fall off the tree, and the tree goes dormant for the winter so that has everything it needs inside of it to stay alive for the rest of the winter. So this is a prism. I don't know if anyone's ever used a glass prism before. If we were in lab together this semester, you would be using those at some point in time. And it's just a glass piece that is in this kind of triangular pyramid shape. And what we're going to do is we're going to pass light into it. And when you pass light into it, it's going to reflect. And since this is clear, it's not absorbing anything. It's going to reflect all of Roy G. Biv. And that's how we get a rainbow. So rainbows happen often after it rains. So there's some water droplets left up in the sky and the sun shines through them. That's one way we get a rainbow. You might see a rainbow in your house depending on like the cuts of glass in maybe your door windows and light shines through. Prisms, anyone ever had them kind of hanging? Or crystals hanging. If light hits them the right way, it's going to give off a rainbow. Another place you kind of see rainbows sometimes is in a puddle of water that might have some type of ethane in it, or propane or butane or something in there that's a gas is formed. Sometimes you can actually see the rainbow there as well. So we're going to stop on this particular video, and we'll catch up on the third video, kind of talking about what is photosynthesis and look at the very specifics of what's happening in our reaction that we looked at a little while ago with carbon dioxide and water making glucose and oxygen.